Welcome to the lecture entitled Scientific Methodology, the Hypothetico-Deductive Method. I'm Andrew Chapman. In this lecture, we'll cover 6 topics. 1. From demarcation to methodology. 2. What is scientific methodology? 3. Baconian narrow inductivism. 4. The many failures of Baconian narrow inductivism. 5. The creativity and probability of science. And 6. The Hypothetico-Deductive Method. Science can't critically examine itself. That's the job of philosophy. And since science can't critically examine itself, it's not able to answer what is perhaps the most important question about itself, which is the question, what is science? Answering precisely and adequately the question of what science is would require finding some criterion, some standard or measure that all things that are science meet and that all things that are non-science fail to meet. Such a criterion would demarcate or separate science from non-science. The search for such a demarcation criterion, that is, for a standard that all science meets and that all non-science fails to meet, is at the heart of, and is the jumping off point for, the history of the philosophy of science, as well as any systematic study of the philosophy of science. This search for a demarcation criterion is known as the demarcation problem. One of the reasons why the word problem is attached to the search for a demarcation criterion is because finding such a criterion has proven historically to be very difficult. Finding a demarcation criterion whose foundations are plausible, that accurately separates fields into science and non-science, and that is possibly employable, has proven almost impossible. 2 intuitive demarcation criteria, known as verifiability and falsifiability, quickly fall apart when they're examined closely. Verifiability cannot possibly be the demarcation criterion, as it makes science too empirical to the point that the criterion undermines itself. Falsifiability cannot possibly be the demarcation criterion, as falsifiability is impossible. Nothing can possibly be falsified by empirical evidence, and this was shown by the Quine-Duhem thesis. Our reason for wanting a demarcation criterion, in order to determine the essence or the nature of science, is nonetheless an important issue and a worthy project. Fortunately for us, finding a demarcation criterion directly is not the only way to approach the issue of determining the essence or nature of science. The demarcation criterion, the issue of correct scientific methodology, and the issue of what counts as progress in science are all bound up with one another in such a way that a solution to any one of these issues reveals the essence or the nature of science, and hence is a solution to the other 2 issues as well. Finding a demarcation criterion would tell us about the essence of science, and then we could use our knowledge of the essence of science to figure out a methodology and a standard of progress for science. But if we can't find a demarcation criterion directly, we could search for a scientific methodology, and from there determine the essence of science. Once we know the essence of science, we could get a demarcation criterion and a notion of progress. Or, if we couldn't find a demarcation criterion or a methodology, if we could find a standard of progress, that would tell us what the essence of science was, and we could use our knowledge of the essence of science to find a methodology and a demarcation criterion. In this lecture, we're looking at the notion of a scientific methodology, so it'll help us to understand in broad terms what a methodology even is. A scientific method or methodology is an ordered set of steps. Those are steps that have to go in a particular order that a scientist ought to follow in order to achieve scientific answers to scientific questions and in order to make scientific progress. Notice that the word ought is in the definition of a methodology. A scientific methodology prescribes what a scientist ought to do. Or, in other terms, a scientific methodology is normative. It doesn't just describe what scientists actually do. It's normative in that it prescribes what scientists ought to do. Since there are many different potential scientific methodologies, scientists and philosophers of science will need to determine which is the best scientific methodology and whether different methodologies should be employed in different circumstances, or instead whether there is one methodology that can be practiced by all scientists and all special sciences. We can rate a scientific methodology's merits according to 4 central criteria. 1. Whether use of the methodology produces valuable scientific results. 2. Whether the methodology is generally easy to employ. 3. Whether the methodology, at least sometimes, matches current scientific practice. And 4. Whether it is even possible to employ the methodology. Sir Francis Bacon was a philosopher, a scientist, a statesman, and an author. He argued for the possibility of a purely scientific knowledge, a knowledge that could be gained via a scientific methodology. He was the father of modern science and was the first to create a generalizable, systematic scientific methodology, so it helps in understanding the quest for a scientific methodology to start with Bacon. Bacon's scientific methodology has a complicated name in the literature. It's known as narrow inductivism, and it's not important why it has that particular name. The term here, Baconian, of course, just means related to Bacon, or coming from Francis Bacon. Here is Bacon's narrow inductivist scientific methodology. Step 1. Collect data. Call all the data that you're collecting D. Step 2. Classify the data into appropriate subsets. Call those subsets D1, D2, D3, etc. Step 3. Form a hypothesis, call it H, from the appropriate subset or subsets of D. Step 4. Draw implications, call those I, from the hypothesis, H. These implications are things that would be true if the hypothesis were true. Step 5. Perform tests, T, of the hypothesis, H, by determining whether the implications, I, hold. And then step 6. If the implications, I, hold, then the hypothesis, H, is confirmed. If the implications, I, don't hold, then the hypothesis, H, is disconfirmed and you return to step 1 and start collecting data. So let's apply this very simply to the question, why do unsupported objects fall? Step 1. Collect data about objects, about what changes when they're unsupported, about how they fall, etc. Step 2. Classify the data into subsets. For example, maybe you'd have one subset that includes all the data about objects when they're falling, and all the data about objects when they're supported would go into a different subset, etc. Step 3. Create a hypothesis from all of this data. Your hypothesis might be that the natural position of objects is on the ground, and objects do their best to reach their natural position. This hypothesis might sound somewhat strange to our contemporary ears, but this is essentially Aristotle's picture of why objects fell, and this was the picture that was in vogue for about 2,000 years. Step 4. Draw an implication from the hypothesis, something that would have to be true if the hypothesis were true. So your implication might be an unsupported object in water will move through the water toward the ground, since the ground is the natural place for that object. Step 5. Test the hypothesis by seeing whether the implication is true. So you might drop objects into water to see whether they move through the water toward the ground. Step 6. Analyze your data. Well, a feather was dropped into the water and it just floated there, so that seems to be not in line with the implication. That means that the hypothesis must be false. Return to data collection. Seems like a plausible scientific methodology. And in fact, this is the scientific methodology that's enshrined in colorful posters in science classrooms in public schools around the country. Maybe you've seen something like this. This was a poster that was just the clearest one that I could find when I did a search for posters that I could buy to put into my science classroom as a public school science teacher. What do you want to learn? Go do some research. The research is your data collection. Form a hypothesis. Experiment there would be the testing of our test implications. Then analyze to see whether the data from your experiments is in line with or out of line with the test implications, and then form a conclusion from that data analysis. If your data is in line with your implication, that shows that your hypothesis is true. If your data is not in line with your implication, that shows that your hypothesis is false. Return to 1. Enter Carl Hempel. Hempel was a 20th century philosopher of science aligned with logical positivism and logical empiricism. His most enduring contribution to the philosophy of science is what's known as the deductive nomological theory of scientific explanation. In this lecture, we're not looking specifically at scientific explanation, but instead at scientific methodology, which, while related to explanation, is a separate sort of thing. What we're saying here, though, is in line with his overall deductive nomological theory of explanation. Hempel thought that there were a number of problems with the structure of Baconian narrow inductivism, and he laid out these problems during his career in formulating his own response to narrow inductivist methodology. Let's look at 5 of the biggest problems that Hempel laid out. Now remember, these are problems for Baconian narrow inductivism. So problems for the view of scientific methodology that we've just looked at and applied. The first problem, says Hempel, is that this first step that we're supposed to engage in, go collect data, is impossible. It's impossible because there's an infinite amount of data out there, and we have absolutely no guide, since this is the first step of our methodology, for which data we're supposed to collect and which data we're just supposed to ignore. So, says Hempel, are we to examine, for example, all the grains of sand in all the deserts and on all the beaches? And are we to record their shapes, their weights, their chemical composition, their distances from each other, their constantly changing temperature, and their equally changing distance from the center of the moon? Are we to record the floating thoughts that cross our minds in the tedious process, the shapes of the clouds overhead, the changing color of the sky, the construction and the trade name of our writing equipment, our own life histories and those of our fellow investigators? All these and untold other things are, after all, among all the facts up to now. Now, if you're saying to yourself, well, of course we wouldn't collect all of that stuff, we would only collect the relevant stuff. Well, relevant to what? We don't yet have a hypothesis on the table. This is supposed to be the first step. Go collect data. If this is the first step, then we can never possibly get started in performing experiments, in formulating a hypothesis, in drawing implications, because there's too much data out there and there's always infinitely more data created. What we need is some sort of proposed solution before we can even get going in collecting all of the relevant data. The relevant data here, what counts as relevant, needs to be determined, Hempel says, by an antecedent hypothesis, a hypothesis that's already on the table. But remember that, according to Baconian narrow inductivism, hypotheses get derived only in step 3 of the process. Steps 1 and 2 deal with data collection and data classification. That's a problem. Problem 2, says Hempel, is that the second step of Baconian narrow inductivism, classified data, is also impossible, since there are infinitely many ways of classifying data into different subsets. Says Hempel, a set of empirical facts can be analyzed and classified in many different ways, most of which will be unilluminating for the purposes of a given inquiry. Thus, if a particular way of analyzing and classifying empirical findings is to lead to an explanation of the phenomena concerned, then it must be based on hypotheses about how these phenomena are even connected. Without such hypotheses, analysis and classification are blind. Notice here that the problem is similar to the problem with data collection. Unless we have some guide regarding how we're supposed to classify data, any guide at all, which classifications are relevant to our investigations and which are irrelevant, the process of data classification will be endless. Problem 3. Step 3 of Baconian narrow inductivism, form a hypothesis, is impossible, since there's no possible merely mechanical process that takes as inputs pieces of data or classified sets of data and that produces, as an output, a scientific hypothesis. Imagine that I put on the table in front of you a whole bunch of data, and I said, create a hypothesis. You'd need to know what method you were supposed to employ in dealing with this data in order to form a hypothesis. Hypotheses don't just fall out of data. They're not just there present in the data. We need something more, something human, in fact, in order to come up with a hypothesis. Says Hempel, there are then no generally applicable rules of induction by which hypotheses or theories can be mechanically derived or inferred from empirical data. The transition from data to theory requires creative imagination. Scientific hypotheses and theories are not derived from observed facts, but invented in order to account for them. They constitute guesses at the connections that might obtain between the phenomena under study, at uniformities and patterns that might underlie their occurrence. Happy guesses of this kind require great ingenuity, especially if they involve a radical departure from current modes of scientific thinking, as did, for example, the theory of relativity and quantum theory. Problem 4. Step 4 of narrow inductivism, draw implications, is impossible, since an infinite number of implications follow from any given hypothesis. So even if you could come up with a hypothesis, which we've already seen is impossible, according to Baconian narrow inductivism, there are still infinitely many things that can be true given any particular hypothesis. So how do you come up with the relevant implication? So for example, if I have a hypothesis that's explaining where my cookies are going to, and my hypothesis is the dog is stealing my cookies, then I can equally validly draw any of the following implications from that hypothesis. Here's one implication. If I leave the cookies out and the dog is around, then the dog will take the cookies. That's an implication. Here's another one. If I leave the cookies out and the dog is around, then the dog will take them, or the birds will steal my car. Here's another one. If I leave the cookies out and the dog is around, then the dog will take them, or the cat will tap dance. Here's another one. If I leave cookies out and the dog is around, then the dog will take them, or the horse will speak. For any true statement, just give it the variable p for right now. All possible statements of the form p or q will also be true, no matter what q is, no matter whether q is true or false. So here's an example. It's true that my name is Andrew. We know that that's true. Given that it's true that my name is Andrew, then it's also true that either my name is Andrew or Abraham Lincoln invented the light bulb. That's true because only one half of an or statement has to be true in order for the whole statement to be true. This sort of or introduction, or just tacking an or statement onto an already true statement, always preserves truth. Take any true statement you want. The sky is blue. Tack any other statement you want onto it with or. The sky is blue, or ants rule the earth. That statement is still true. It's true that either the sky is blue or ants rule the earth. Now, given that we can always create infinitely many true statements given any one true statement, that means that for any potential implication that follows from some hypothesis, we can create infinitely many other implications that also follow from that hypothesis by just tacking ridiculous or not ridiculous or statements onto our original implication. Now notice the problem here. There's no mechanical process that tells us which are the correct implications and which are the ones that we can ignore. All Baconian narrow inductivism tells us to do is get an implication. Well, an implication is just something that has to be true if the hypothesis is true. And there are infinitely many things that have to be true given any particular hypothesis. The final problem we'll look at. True implications don't confirm hypotheses, so the conclusion of Baconian narrow inductivism is simply false. It's a misunderstanding of how logic works. So while it's true that if a test is performed and an implication is found to be false or at odds with the result of that test, the original hypothesis must be false. It's not true that if the results of the test are in line with the implications, then the original hypothesis is confirmed. This is a fallacious form of reasoning that's known as affirming the consequent. When one affirms the consequent, then they conclude from the truth of the then side of an if-then statement that the if side must also be true. But that form of reasoning doesn't work in most cases. Consider a few examples of when this breaks down. If something's a cat, then it's a mammal. That's true. Therefore, if this thing's a mammal, then it's got to be a cat. Well, not necessarily. It could be a giraffe or a dog or a platypus. If it's a square, then it's a rhombus. That's true. Well, we know it's a rhombus, therefore it's a square. Well, not necessarily. There are all sorts of rhombuses that are not squares. If he's her husband, then he's married. That's true. You can't be a husband without being married. He's married, therefore he's her husband? Well, not necessarily. Could be somebody else's husband. If she was murdered, then she's dead. True, all murdered people are dead. She's dead, therefore she was murdered. Not necessarily. In fact, most dead people were not murdered. So, given the truth of a test implication, it's just not the case that the hypothesis is confirmed. It does tell us something positive about the hypothesis, but it doesn't tell us what Bacon thinks it tells us. Hempel noticed a couple of things about scientific practice that were missing from Bacon's account. The first is that science is creative. In 1865, Auguste Kekulé published a paper hypothesizing that the structure of the benzene molecule was circular or ring-like, that it doubled back around on itself. According to Kekulé, he had come up with this idea of the structure of the benzene molecule during a daydream in which he saw a vision of a snake biting its own tail. Kekulé's hypothesis was put to the test, and sure enough, his hypothesis was correct. Hempel, quite taken with this story and countless others like it, recognized that science is not a merely mechanical process, as it was described as being by Bacon. One that can be fully formalized and systematized. Science requires substantial creativity, not only in solving individual scientific puzzles, but also in creating hypotheses and determining test implications, even in coming up with the sorts of things that we might want to investigate. Scientists should use and do use, says Hempel, whatever creative means they please when creating hypotheses and determining test implications. And this really does mean any creative means that they please. So take a nap and dream, or go out into a field and look at the shapes of clouds, or have too much to drink, or talk to friends, whatever. Any creative way of coming up with things, that's great. But science is still grounded objectively in the actual world, despite the creative creation of hypotheses and implications, because these creatively invented hypotheses still have to be tested against the empirical world. So Hempel isn't saying just make up whatever you want. He's saying make up whatever you want and then test it. Hempel also recognized that Bacon was claiming that scientists are much more certain about their conclusions than they actually are in scientific practice. Scientists only ever have a partial picture of reality, and no matter how good the tools of science become, no matter how much technology progresses, there will always be data relevant to any scientific hypothesis that still has not been collected. So this isn't a problem with science. It's not a problem with the data that scientists use or the tools that they use to collect or analyze that data. It's just a fact of the investigation that science is a part of. Consider the case of the color of swans. This is a case that has become very famous in the philosophy of science. For a long time, every time a swan was observed, that swan was white. This led scientists to believe that all swans were white. However, they couldn't know for certain that all swans were white, as they hadn't seen all of the swans, and there could have been a yet unobserved black swan somewhere out there. And Australia is where they were hiding, in fact. There were, in fact, and still are, black swans. They just hadn't been observed yet. Thus, given the nature of the natural world and of scientific evidence, scientists can never be certain that their conclusions are correct, although they can be justified in believing that their conclusions have a high probability of being correct. Now, this isn't a criticism of scientists. This is a criticism of Baconian narrow inductivism. Narrow inductivism was what claimed that scientists can be certain of a hypothesis given some amount of evidence. But, as Hempel recognized, no, scientists can't be. Thus, Hempel proposes an alternate scientific methodology in response to all of the problems that he outlined with Baconian narrow inductivism and the things that he recognized about how science is actually practiced. Step 1 of the Hypothetico-Deductive Method. Observe the world and creatively decide on some problem that you'd like to solve. Notice right away we're in a very different place than we were with Baconian narrow inductivism. This doesn't say gather all of the data. It says be creative. 2. Invent a hypothesis, H, via a creative act of the imagination. Do whatever you please, make something up. 3. Decide which testable things, I, are implied by the hypothesis, and decide these, of course, creatively. Go out and collect some data, D, that's relevant to H and I. Notice that data collection shows up fourth rather than first. Data collection is here guided by the antecedently existing hypothesis and test implications. Now there's a guide for data collection. And 5, see whether the data collected is in line with or not in line with the implications. If it's in line with the implications, then H has been rendered more probable. Notice, that's not confirmed, it's just rendered more probable. If the data is not in line with the implications, then H has been disconfirmed. Go back to step 2, invent yourself a new hypothesis. So let's apply this methodology to the same question that we applied Baconian narrow inductivism to. Why do unsupported objects fall? Step 1. Look around and notice that unsupported things fall. Decide, well, you'd like to figure out why that happens. Step 2. While perhaps watching a movie in which lasers play a substantial role, wonder whether, hey, maybe lasers have something to do with unsupported things falling. Create a hypothesis that ties together falling objects and lasers. Step 3. Since a laser is just a kind of light, you could use appropriately sensitive light sensors to test whether lasers come into the mix when an unsupported thing starts to fall. Step 4. Run some experiments with falling things and your light sensors. And then step 5, see whether the data that you've collected gives any reason to think that there's a change in light when things fall. If there is, your hypothesis is rendered more probable. If not, and unfortunately for us there's not, it'd be cool if lasers made things fall, your hypothesis is refuted and return to 2. Notice how different this application of a scientific methodology is to the same question that we were asking before. When we compare Bacon and Hempel, 2 things stand out. The hypothetico-deductive method is based on Hempel's recognition of many different failings on the part of Baconian narrow inductivism, but the central differences between the 2 methods can be boiled down to 2 things that Hempel noticed about actual scientific practice, and these are the 2 things that we've already noted: that science is creative and that scientific conclusions are probabilistic rather than certain. Science is creative in that determining which problems to investigate, creating a hypothesis, collecting data, and determining test implications are only possible with the infusion of at least some level of creativity on the part of the scientist. Scientific conclusions are probabilistic in that since any piece of evidence is always consistent with more than one hypothesis, and since scientists can never collect all of the possible data, scientists can never be certain that their conclusions are true, although they can be pretty sure. In this lecture, we've discussed 6 topics. First, we've discussed a move from demarcation to methodology. Second, what is a scientific methodology? Third, Baconian narrow inductivism. Fourth, the many failures of Baconian narrow inductivism. Fifth, the creativity and probability of science. And sixth, Hempel's hypothetico-deductive scientific method. Thank you.